Thank you very much. I appreciate the opportunity to come here and give a talk, and want to begin by acknowledging that the subject I'm talking about is really at the intersection of a huge revolution that's ongoing in stellar astrophysics between many different capabilities. And so as a result, of course, this work reflects the efforts of a large number of teams. I'm going to be discussing work that comes from the Kepler Asteroseismology Science Consortium, the group that analyzes light curves to infer time domain information from that satellite and others. Also from the Apogee spectroscopic survey, which involves a very large database of abundances and information, and more recently in folding in information from the Gaia team. I particularly wanted to call out some of the efforts involved here. Graduate student Joel Zinn, who I've done work with, and much of the Gaia work has been done on the base with Joel, comparing seismology and Gaia data. Also Daniel Huber and Dennis Stello, and the entire APOCAST or Apogee Kepler collaboration for many of the results that follow. Now, what I'm going to be beginning with is I always like to look at a motivation, and one of the things that's been particularly striking is that you have a rich set of information both on kind of chemical evolution and I would argue on galaxy formation when you look at this kind of new generation of time domain and spectroscopic data that we have. On the left-hand side, traditionally people like me have treated this entire periodic table as being hydrogen, helium, and iron, right? That's basically been the entire periodic table that we have. And one of the really striking things in the era of these spectroscopic surveys is we're now exploding this into multi-element mixtures where we can really look at the trends of chemical evolution and their origin in time. This is a challenge. It also means from the point of view of people like me that you would very much like to be able to infer ages and other things for properties extremely reliably in order to be able to trace this origin. That's actually one of the motivations for my interest in the topic of seismology, which I'm going to try and convince you does let you measure ages precisely of old stellar populations. On the other side, you can also look at things like this beautiful simulation from the Hopkins Research Group, which may or may not be simulating. We'll see. If not, I never trust videos much on these presentations, so I'm going to assume that I don't have to work. Real time. Yeah, yes, exactly. In any case, were you to see this, you'd see a bunch of forming things, but fortunately I don't worry about that. So trust me, galaxies form and we'd like to see how. Now, much of this work focuses on red giant spectroscopy and astroseismology. And I think the reason for this is pretty clean. Red giants are incredibly luminous, and that implies if you wanted to trace galactic populations over large distances, you want luminous stars to do it in. This is kind of showing you a map from a paper I was involved with Melissa Ness and collaborators, trying to do basically a tagging exercise for stars in the Apogee survey. And the point is we're actually measuring ages across the galaxy. We can use this do this using red giants. We're not just restricted to the solar neighborhood, which previous studies were. You also can obtain really powerful information in the spectra. It turns out the red giants have a lot of information about their abundances and their physical conditions in the atmosphere from traditional spectra, and completely accidentally, but fortunately, their time domain spectra are also information rich. I contend that every cool red giant is an oscillator that we can detect in the Kepler system, and if they're not oscillating, say almost everyone, if the handful that are not, are exceptionally interesting, because they should be, right? So this is remarkable, remarkable data. Now the problem with giants is that pre-astroseismology, this is roughly what they look like from a spectroscopic point of view. They're all red, they're all very, very similar, and it's almost impossible to tell one from another or their age. And this is basically illustrated here. These black lines represent traditional isochrones, or this is sort of 3, 6, and 12 gigayears, roughly speaking, or 2, 6, and 12 gigayears. And then what you're seeing here is near the turnoff, you have a lot of discriminating information based upon the traditional properties. When you're giants, they all converge together. They're impossible to tell apart. The blue and the red represent the effects of chemical composition. So the observed properties of giants are enormously sensitive to their composition, enormously insensitive to their age, and so as a result, it's a terrible way to get ages to look at giants traditionally. However, astroseismology comes into the picture, and I've sort of settled on this one-slide summary of astroseismology, and we'll see how well this works. You start out with turbulence in the envelopes of stars. This is a gorgeous image from the Swedish Solar Telescope, a snapshot of the sun in time. This turbulence creates waves, sound waves and water waves in particular. These waves then basically propagate. There's a huge density gradient in stars, a factor of about 10 to the 8th between center and surface in the sun. They're refracted and they bend and they come back. And if you have the right critical initial angle, you create a standing wave pattern. And the standing wave pattern creates alternating patterns of brightness and darkness in these stars. In the sun, we observe 10 to the 5th such distinct modes in the study of helioseismology, which is 10 to the 7th existing, 10 to the 5th individually identified, I think is the order. But there's a huge, huge pattern of these things that you can really get this incredibly rich information on. In the case of stars, where you're looking at the integrated light, you can't see all those modes, but you can see the low order modes, the ones with a low number of L. You count the number of nodes with latitude, the spherical harmonic degree L, numbers up to 3 you can actually observe in these stars. These are actual Kepler time domain data showing you the light curves of objects with different radii. You notice the smaller giants have low amplitude, high frequency oscillations. The larger giants have high amplitude, low frequency oscillations. If you take a Fourier transform of this data, this is a little bit of a cheat, these aren't the same stars, but the sequencing is the same. You notice that you have a very characteristic pattern. You see a turbulence background or a granulation background. You see individual spikes, these places where these standing wave patterns are set up. You observe that the frequency of maximum power appears to scale with surface gravity, as does the spacing between the individual modes. These are they're mostly pressure modes, as I'm going to get to. You can actually see some of the modes which have an imprint of the G mode signature on the core. But these are the first order deep convective envelopes, and mostly pressure modes or sound waves that you're actually observing in these stars. And so you have a characteristic pattern where you can already see that there's 2 distinct families of observables, both of which observationally scale with the radius. If you kind of break it down, this is again a diagram I love to show because this is Kepler data. Now for the star 16 Sig A, if I were to superimpose a spectrum of the sun, it would look a lot like this. The Kepler data is almost of comparable quality, which is amazing. You notice there's a characteristic frequency of maximum power. And analytic theory doesn't give us much guidance on this, but empirically, roughly speaking, we think this ought to scale with the acoustic cutoff frequency in the atmosphere, which is tied to the surface gravity. So approximately speaking, this frequency of maximum power ought to scale approximately as log g. You also observe these frequency spacings, and analytic pulsation theory does make a prediction that this spacing ought to be related in the limit formally of infinite n and homology as the mean square root of the mean density of the star. Right? So characteristically, you think that this autoscale is m over r cubed, this autoscale is m over r squared. We're astronomers, we can solve 2 equations and 2 unknowns, and you have independent information on m and r if you do this. If you add spectroscopic information, you can also infer ages. And so basically we're contending that you can measure these spectra in virtually all giants. You have a simple theoretical framework in which you can extract masses. And if you can extract masses, then all of a sudden this red giant branch age problem becomes tractable. These are now the different age systems where my observables are gravity and mass. You notice the different ages are very well separated in mass. Chemical composition is a comparably small signal, and as a result, this is a great promise for measuring ages in a population of intrinsically luminous objects with a good fundamental theory basis. Yes?
Is the frequency splitting due to rotation?
There's also a splitting due to rotation. I had to make a tactical choice to suppress that despite my love of rotation and my strong interest in that. In fact, if I just showed you the previous diagram, each of these individual peaks is rotationally split, and that's the rotational splitting of each of those individual modes. And the modes that probe the core and the envelope, you can separably distinguish the rotation of the core and the rotation of the envelope and the frequency spacings, which is a gorgeous, again, unanticipated development in this field. So given this independent mass information, this kind of gives you the characteristic results, and the first generation of this result just shows you how much your information improves when you include seismology. On the left-hand side, this represents the observed stellar properties in the first release of the Kepler input catalog and the Kepler fields, where this is based on photometry, and you can see that there do exist giants, but there's just a giant blob, and it's hard to see any interesting structure. You then add spectroscopic constraints. The giant branch begins to tighten up, but it's hard to see individual data. And if you add astroseismic information, now you all of a sudden get an extremely fine picture, basically basically the field color magnitude diagram starts to look like a cluster. In other words, you start to be able to see individual features and timescales in this data set. Now the next piece here actually has to do with looking in detail at the core. This will be the one time I talk about the detailed frequency pattern because I think the physics is beautiful and the implications are also very, very clean. These are the observed power spectra of a dwarf, which is the kind I showed you, the nice even spacings, and of a red giant. And one of the very first things we saw in this is that there's an utterly striking morphological difference between these. This is actually, by the way, part of the reason why we did not necessarily see seismology of giants from the ground. The ground-based seismic data for giants looked complicated, the ground-based giant data for dwarfs looked simple, and we thought the giant data was just mistaken, it was corrupted or something like that. It turns out that it's real physics. So this is a pure P-mode signal. This is a pure sound wave signal where you predict these almost evenly spaced modes. We believe that this messy pattern here is actually due to the presence of mixed modes. In the sun, the G modes, the water waves, have periods of a few hours. The P modes have periods of a few minutes. As the structure evolves, the two combs have comparable frequencies, and what you have happening to you is the same thing as having two pendulums operating with almost exactly the same frequency next to each other. They actually talk to one another. You create modes of mixed character. And this is seen here. This is basically a snapshot in time. This is a pure G mode pattern. This is the predicted mixed mode pattern that you should see, and this is the real observed pattern that you see in a red giant branch star, which shows these patterns. This allows you to use some of the modes, the ones that are very, very strongly influenced by the G modes, where the frequencies line up right, to learn about the core, and other modes, where the G modes are far away, to learn about the envelope. So it's actually a beautiful piece of physics. What this means is that you can actually look at the frequency pattern and tell what's happening in the core. This is what's called Nichelle Diagram. The idea here is you take all of the frequencies and plot them against that spacing that I showed you. And if you had perfectly evenly spaced things, you would have a whole series of things that would just be a vertical line on this diagram. If they had different absolute frequencies, there was just a 0-point offset, you'd have parallel lines, and that's what you see for dwarfs. L equals 0 is here, L equals 1 is here, 2 is here, 3 is here, and so forth. Right? These are perfectly, almost perfectly parallel sequences. When you get to the subgiants, they start to cross, and for individual modes, they start interacting, but most of them don't. That's why you get this characteristic sawtooth feature here. Giants are complicated and clumps are really, really messy. We can do this for every one of these stars, which means we can tag every red giant not only with a mass and a radius, I would contend, but also with a core structure. Objects that have core helium burning structures have a different density profile and a different frequency pattern than objects with a degenerate core, first descent giant branch stars. Now the challenge here is to go from initial promise to results. And what I'm really going to be reporting on here is initially it looked like this stuff worked at an interesting level, and I'm trying to convince you it works in detail at a quantitative level as opposed to a qualitative level. And so the issue here is, first of all those scaling relationships I told you had twiddles in them. That's because they're not exact, right? So if you actually want to have a real measure of the mass, you have to account for the actual structure of the star when you're interpreting the frequencies, and you have to check and see whether your assumptions are actually right. The other thing is that you need to make a critical look at the measurements, the uncertainties, and the assumptions that go into this. In other words, when I measure these things, what am I actually measuring when I take a spiky spectrum with distinct frequencies and saying I have a frequency of maximum power? What does that mean when I have discrete frequencies with different amplitudes? And how well can I actually make these approximations? And so to give you an idea of why you might worry about this, this is actually one of the cautionary tales from the first generation of astroseismic measurements we did. These are halo stars. These are the formal masses that we derived from astroseismology for halo stars. And the thing is that we know that halo stars are an astrophysically old population. You can therefore apply an astrophysical prior and say an unbiased distribution of halo stars ought to have masses between 0.8 and 0.9 solar masses, approximately speaking. That corresponds to a Hubble time. Okay? And if you look at the real masses, you notice they're not 0.8 or 0.9. They were 1.1, higher, things like that. And this is indicating that kind of at the 10% level, there may be biases in our measurements. Since the age scales as the mass to a high power, the third power or higher. A 10% error in the mass is a significant error in the age, and therefore, as a result, if you want to make a precision measurement, you have to understand where this comes from. Okay? So the net result of this paper we published last year is the second APOCAST catalog, which has about 6,700 targets with spectra and seismology. In each of these we have masses, radii, and detailed abundance mixtures. And this diagram here is showing their location on an analog of the HR diagram where the y-axis is gravity instead of luminosity. They're color-coded by the structure of the core. The objects in blue are the objects that we believe have a core helium burning source based upon their frequency pattern. The objects in red are first descent red giant branch stars or asymptotic giants, which also lack a dense central core. These are asymptotic giant branch stars going from here to here. You can see the red giant branch bump where the evolutionary tracks double up and come back. You can see the high mass red giant red clump stars, which had a non-degenerate helium ignition. There's beautiful physics encoded in the details and structure of this diagram already, which is a lovely sign of the quality of the data that we have. Now, the differences I'm going to talk about here, as I mentioned, I'm going to talk a little bit about how we do our measurements and our errors. And the other key point is that we no longer adopt naive or simple scalings. We account for the eigenfunctions of the modes when we're computing the mean density. Theoretically motivated corrections to these. And then we also checked the frequency of maximum power relationship, the 0 point, such that it is consistent with fundamental mass data. And it's these two steps that are new, which then lead to an absolute scale that actually holds up, as we'll see, extremely well against data from Gaia. So we want to look at the challenges in the measurements. This is what kind of your real data might look like. And here's your problems. You have a granulation or turbulence background. People who work in exoplanets may know this as flicker, by the way. This is basically related to the convective properties that you're seeing. And you have to be able to subtract off a smooth background somehow to get a power excess, right? So there's a technical challenge associated to how you define that and how you do it. In addition to that, the modes themselves are actually excited stochastically. This is actually a much bigger issue for K2 and for TESS than it was for Kepler, which was observed for 4 years. And that implies as a result that you don't actually observe modes naively in any individual epoch that are equally spaced. It's just they average out over many epochs to an equally spaced set of modes, and you have to account for that stochastic excitation. And the other problem I'll get to is that you are looking at giant fat pixels which contain many stars, and the variability signal can have backgrounds and blends, which actually matters for a significant fraction of the sample. And this is an unappreciated aspect of this problem. So if you just look at the Kepler light curves, you see an R Lyrae or a Cepheid and an awful lot of Kepler light curves, right? And you have to be able to subtract those out somehow. So this is kind of showing you an example of the kind of raw systematics that are present in the data. This is 5 different analysis techniques. And the idea here is this is the frequency of maximum power, this is these frequency spacings, and this is 5 different very well-vetted methods where basically you're taking the average of their measurement relative to the ensemble mean. And the point is that different people have sort of 0-point systematics in their measurements that are kind of at the percent level or a couple percent level. And remember that in these mass estimates, roughly speaking, the mass scales as this frequency spacing to the 4th power, and it scales as this frequency of maximum power to the 3rd power. And so you can produce, kind of 5 to 10% level 0-point shifts with 2% to 1 to 2% level shifts in the measurements. And so the good news is the measurements are clearly good to at least 1% or 2% absolute, and the bad news is that that's not good enough for your purposes. Yes?
Well, I understand new mass you may have the way you measure is kind of vague. But how would delta mu is any kind of spacing? Why is that?
Because the spacing is not perfectly uniform. And so as a result, between modes, and so where you decide that you're going to measure it from one person to another is slightly different, and those deviations from uniformity can change your mean measurement.
But that error would not exist in the fundamental analysis because you're using a true pulsation model.
Well, you would have to correct them. And if you corrected each element individually for a true pulsation model, yes. So this is just the raw measurements, which is to say people look at this comb, they make a judgment of, do I measure the average across the whole thing? Do I measure only the value in the middle? It's those kind of things that produce signals at this level. I'd like to show this just to demonstrate that there are measurement systematics that are real in this data that you actually have to account for.
My feeling is that error is gone. What's the error left?
Well, the error you're left with looks like this. So on the right-hand side, this is basically saying once you normalize out these 0-point differences, this is the delta nu, and like you said, the actual scatter in the measurements is actually now quite small. It's a few tenths of a percent. And so I would contend that from the point of view of that measurement, once you actually account for these differences and deal with them properly, that's a very small source of error. The frequency of maximum power is of order 0.5% or a little bit better than that. And that, again, is an argument that you can standardize these measurements to be on the same system, at least, to that kind of characteristic level. Now, yes?
If you use actual modeling, then why would you use
The reason you do that is if you try to use the individual frequencies, you're only getting a mean density. And so you need some external constraint to separate out the mass and radius effects, and the nu max gives you the surface gravity, which gives you an independent handle on that.
So nu max depends on how you decide the mode and how you, that just is not really theoretical.
Yeah, exactly.
So you're just doing this empirically.
Yeah. So its nu max is basically an empirical measure, and we see observationally that it's tightly correlated with the real measured surface gravities and radii of stars, right? And so the nu max, I want to stress, is a empirical constraint. The delta nu is a theoretical, well-motivated independent measurement. Yeah. Which is why many people in my field hate nu max, but it works incredibly well. It works it works much better than it has any right to work. And so there is actually something very, very deep in that scaling.
that? Is a large system like that.
Well, I would contend it's larger than delta nu, but it's one that we can calibrate out and check against the data.
But it motivates understanding driving and gas.
Yeah.
This is a clean answer.
Yeah.
You're telling us that there is a good answer.
Yeah, there is a good answer, and it's remarkably good across many decades, across stars that are many, many orders of magnitude in scale. Interestingly, the red clump stars are much harder to standardize. And this is a sign of the fact that the red clump stars have much more complicated internal structures, and I would say in this case, I'm going to try and convince you, I think this reflects the fact that our models of clump stars are actually not very good. And as a result, they're not actually good templates to the real pulsation patterns. If you look at the uncertainties, this is another significant change from prior efforts, because what happens is you have people, this is the same problem you have in Spectra, right? Your basic problem goes as follows. You're trying to figure out, based upon a complicated model fit to a spectrum, what your actual uncertainties are, and it's very, very difficult to do a proper analysis of that. And so on the left-hand side, this is how well all the various methods thought they could measure the answers. This is how well they thought they could measure the frequency of maximum power in the spacings. This is how well they actually agreed with each other. There's almost no correlation between the optimism or pessimism of the pipelines and the actual scatter. And so as a result, we took the view that we actually had measured the scatter by measuring the different methods. And in fact, this produces, as it turns out, a dispersion in, say, the masses of open cluster giants that almost perfectly matches the dispersion in the data. And so as a result, we think that our dispersion is dominated almost completely by interpretation of the signal, that's, say, the measurement of the properties, rather than being dominated by the noise in the spectrum, which again is not something we had predicted. The other point that's interesting is for about 25 to 30% of the sample, here for example for red giants, this is the distribution of deviations around the mean, the agreement between methods, and if everybody saw something, the agreement is remarkably good, a few tenths of a percent. But in about 25% of the cases, at least one method failed, and these messy, noisy, real-life light curves had much more scatter. And so as a result, this is a sign that background signals or complications are real, and for at least 20% of the systems you need this. This is one reason why I'm a very strong advocate of using multiple detection techniques to look at this, because individual pipelines will be very wrong about 20 or 25% of the time. Individual methodologies, because of the complications of blends or activity or artifacts in the data or whatever it is that's producing these signals, which again was a surprise to me. It was this much, but in fact it really is about a quarter of the stars in the Kepler field, which are very well studied. And it's more stars, by the way, in K2 and TESS. The last bit is theoretically, yeah.
So something to do with that field or that pixel.
Yeah, so you can go in and look at it, and there's a RLI ray that's in the background that gives you a spike in the power spectrum, and if you can't remove that spike, it messes up. Yeah, eclipsing binaries, RLI rays, Cepheids, things like that, and for the kind of scale we're talking about, it's actually quite consistent. It's actually a generic problem with time domain studies in general, is that the amplitude of variability is only loosely correlated with the brightness of the source. And so as a result, you can have problems with background blends in time domain studies that are quite severe. It's the same.
Good small pixels.
Yeah. Kepler's are 4 arc seconds, which is pretty big. TESS is 24 arc seconds, which is a bit more of a technical challenge. Resolution of the human eye. So anyway, if you look at the theoretically motivated corrections, the argument here is if we have a theoretical model, we can predict the frequency pattern, we know which radial order we're looking at, and we can know what the spacing maps onto the actual mean density. And this is showing you that for red clump stars, these kind of corrections are of order unity, meaning that basically they scale extremely well relative to the sum. And for red giant branch stars, there's a significant correction which actually explains that mass discrepancy I talked about with the halo stars. That basically you have of order a 10% level bias in the masses for the red giants. A good way of thinking about this is there's a lot of mass in the red giant in the deep core, which is not felt locally in the envelope and reflected in the eigenfunctions, I think is the way that I like to think about it. If we now apply these corrected scaling relationships, this shows you the raw data in 2 star clusters, NGC 6791 and NGC 6819. The dashed lines are strong priors from eclipsing binary measurements. We contend these are the real masses that we expect for these red giants. These are the first descent red giant branch stars in the young cluster and in the old cluster. The blue are the core helium burning stars. If we apply theoretically motivated corrections, you notice that we agree extremely well with the observed mass scale. And the other interesting thing here is look at the clump stars. You notice the clump stars in this cluster have almost exactly the same mass as the giants. The clump stars in NGC 6791 have almost exactly the same masses as the first descent red giant branch stars. We detect almost no mass loss at all on the first descent red giant branch between these 2 populations, and we think this is absolutely a solid theoretical result. So as a result, we had traditionally thought, based on globular clusters, that there's a huge amount of mass loss on the first descent giant branch. It appears that's only true, bizarrely, in metal-poor populations. Metal-rich giants, which by every right of logic ought to have more mass loss, have less. I do not know why. That's a result.
What's the scattering?
The dispersion here is about 0.04 solar masses, which is roughly, the reduced chi-squared you can just see by eye is of order unity in this thing. So
and most of the change is due to the application of stellar models?
Yeah, between this and this is the corrections due to stellar model physics. That's what's moving you from the left to the right-hand panel.
One reason why it might be the case, so it's efficient, the cooling is less efficient when you have less levels.
Yeah.
Yeah.
So maybe also the globular clusters are strange systems. It may be something else is going on in globular clusters that we've used as our template. But it's also clear that we see the same phenomena in the alpha poor and alpha rich red giant field giants. The alpha poor giants have masses where the distributions look very, very similar to the clump. And the alpha rich giants and clumps have different masses, indicating clear evidence of mass loss. So it appears to be present in the field as well as the clusters. And so now I'm going to switch over a little bit to the galactic formation side as to what you can do with this, because there's been a whole series of developments related to the Apogee mission, kind of tying this to chemical evolution, adding the age dimension. I think that those results are interesting and worth calling out. Now, when I do this, I have to remember as follows. We have these big spectroscopic surveys. There's asteroseismology and ages, Gaia and kinematics. But as somebody who's been around in the field enough to notice, we did do things before we had these space missions, right? We actually knew things about these subjects before. And if I wave my walker around about my papers, whatever, not being cited, that's part of it. But even so, it's important to acknowledge, put this in a context about this kind of work here. And so one of the first clues we had that something interesting was going on was the very weak local age-metallicity relationship. The beautiful work by Edvardsen et al. Kind of set the standards for this. And the argument was that initially you might think that, well, the galaxy formed stars where gas was dense. In the middle of the galaxy, it's a lot of density of gas. So you'd form your stars first in the middle of the galaxy. You'd build up a nice metal abundance there. You'd have a lower metallicity when you went further out. So you'd have some kind of beautiful monotonic mapping between age and metallicity at any given place in the galaxy. The real galaxy shows nothing like this. This is iron, alpha, and barium. Remember, this is only the solar neighborhood, using basically Hipparcos data, beautiful parallax data. And at fixed metallicity, you see an incredibly wide smearing of ages. And so this is an evidence that there's radial mixing. Galactic populations move radially within the galaxy, and this kind of scrambles what otherwise in principle should be a clean signal. Now the second clue we had, and this is again work by Thomas Bensby, again in the solar neighborhood, the open and filled symbols represent basically thick and thin disk stars. We've now expanded our numbers of entry on the periodic table from 1 to 2 instead of just iron. It's alpha and iron. And the argument here is that alpha to iron is a measure of the relative importance of core collapse supernovae and basically a supernova 1As. And if I look at these two different sequences, I see that I start in my very metal poor populations with a high alpha, that's few 1As. I then transition to more 1As down here. And the fact that I have multiple sequences here is telling me something about the time scales. The argument is that I have different time scales for the transition between these two branches, which produces multiple populations. Okay? Now, if you want to go beyond that, the Apogee survey, which I'm sure that you all have heard about here, has been giving us a fantastic resource. It's a full H-band spectrum, a resolution of about 22,000. It gives you basically an automated pipeline analysis. There's almost 400,000 stars with detailed abundances in the latest release. These were beautiful for Kepler because it turns out that if you've ever looked at the Kepler field, there's 21 individual CCDs. An individual apogee plate is almost exactly the size of one of those plates. And so you can get 300 stars at a time by just dropping a plate on basically a Kepler field. And if you wanted to measure red giant asteroseismology and you wanted a sampling cadence, it turns out the answer is 30 minutes, which was the exoplanet one. So basically, if you designed a red giant astrophysics mission, you would have designed Kepler. And if you wanted to design a mission that had good spectroscopic follow-up, you would have picked their field. So it's just completely perfect from our point of view. It's important to note that apogee recalibrates after the fact. Their temperatures to be on an absolute scale and their gravities to be on an absolute scale. You get individual element abundances, and so you also have other surveys like LaMost and Galam, and I'm going to focus on apogee because the data has absolute calibrations that actually make it attractive for absolute ages and things like that. This is showing you from a kind of a beautiful paper by Hayden and collaborators. Sorry, the caption got knocked off there. This is kind of showing you our local population in this alpha to iron versus iron plot as a function of height above the galactic plane and distance from the galactic center. This is showing you how much our knowledge has changed here. You can see that you have the alpha pore sequence is migrating to successively different metallicities. Joe's done a lot of beautiful work on tracing out these sort of mono age and metallicity bins. You also see that the alpha rich populations vary with strength as you go in height above the galactic plane and in position. It's a rich, rich data set that's telling us a lot about how chemistry changes with position. Now, none of this says anything about age directly. This is just chemistry. And so what I'm going to argue is that asteroseismology lets us add age to the dimension, and Gaia lets us add kinematics. Okay? If you go beyond this in a paper that very recently came out by one of my OSU colleagues, Dave Weinberg and collaborators, it actually turns out that even the assumption of a fixed alpha mixture and a fixed iron group mixture dissolves in detail. Okay? So in other words, what you see here is you see that basically the blue and the red correspond to the alpha rich and poor sequences. And this is demonstrating that if I plot these up as a function of magnesium, I see changes in the relative abundances of different heavy elements that are significant. So silicon, for example, does not track magnesium perfectly, even though both are alpha capture elements. You see oxygen doesn't trace magnesium perfectly. You can see changes within the iron peak groups as well. This is telling you again about the detailed imprint of different nucleosynthetic sources. Although interestingly, Weinberg and collaborators make the argument that you can explain these trends within a chemical evolution framework that still has two principal sources, which is core collapse supernovae and supernova 1a. They're just contributing at different epochs at different rates. So basically they argue that this pattern should not be fixed, but that there is clearly evidence that the mixture itself changes. And this is, by the way, accounted for in no stellar models that I'm aware of. Now the next game here is let's go beyond these detailed things to see if we can actually do chemical tagging. And there's really two approaches to dealing with the seismic data. The first of these approaches is to say I'm going to take this seismic data and I'm just going to measure individual ages for individual objects because I have their masses, right? The other argument is let's see if we can use this as a calibration or a training set to apply to all spectra using the techniques of basically chemical tagging. And so initially, now this is an area where I have some philosophical issues, and so there's different methods for doing it, some of which I prefer more than others. I like using the carbon to nitrogen ratio as an age indicator because I understand the physical mechanism. In the cores of main sequence stars, you transform to carbon to nitrogen in the CNO cycle. This is temperature dependent and mass dependent. I dredge it up. A higher mass star has basically less carbon and more nitrogen. I understand the physics of that. You can also take the entire spectrum and look for features that correlate with age. And this can include things that have a physical basis, but more dangerously also things that simply correlate with age as opposed to being driven by age. And that's the defect of this. This is showing you the mass versus carbon to nitrogen in kind of the original apogee sample. And this gives you thousands of calibrators to apply to a very large sample. This is the more recent data we have in the 2018 sample showing you the mass to Cn as a function of metallicity in our sample. You notice that at the very lowest metallicities, this pattern is clearly beginning to break down, an indication that things like extra mixing are changing your signal. As you go to higher metallicities, you see a nice sharp correlation. There are outliers. I have no idea what these stars are over here at all. They're probably binary mass transfer products, actually, given the low masses. You can observe a characteristic flattening at high masses, which is predicted by stellar theory. There's beautiful, beautiful data behind this. If you look at it in more detail, you can see, by the way, that the red clump and the red giant branch have similar but not identical carbon to nitrogen and mass correlations, which means you can apply this not just to first descent red giant branch stars, but even to core helium burning stars as well. On the y-axis here, there's carbon over nitrogen, and the x-axis is the mass as measured by seismology. And so this then can also be used as a full spectrum calibrator. In this case, there's two examples here. There's the effort by Ness et al. To use the apogee sample to basically train on some thousands of astroseismic measurements and measure or infer masses for hundreds of thousands of spectra. On the bottom, the work by Ho, where they actually used an infrared survey, apogee, which had an overlap sample with an optical survey Lamoste, and then they transferred the labels from the infrared to the optical survey and applied it to the entire Lamoste sample of millions of stars that you can actually do this for. So the bottom line is you measure direct masses from seismology, I would argue, for samples of thousands, which you can leverage with these techniques to samples of hundreds of thousands with the proper calibration procedure, individual ages for giants. Now our first surprise was we called the young alpha-rich stars. These things are color-coded by the age. The gray things are old. This is high alpha versus mass. And you notice that most of the high alpha stars, as expected, are low mass and old. But about 4% of them are clearly not. These objects either represent an interesting young stellar population that's chemically old, which would be really interesting if it was present in the galaxy. That's one source. Another source is my mass could be high because I had two low mass stars that merged. I'm an evolved blue straggler, and that will also be present in the sample. The rate of these objects is interestingly high if they're blue stragglers, and I'd argue the chemistry can't work for all of them to be blue stragglers. But in any case, many of them are blue stragglers, binary merger products. Some of them might not be, which would be cool. If they are merger products, there's a lot more mergers than we would have thought of based upon previous population synthesis models. The next thing you can do is you can go into the apogee field, and this is the low alpha sample, this is the high alpha sample, both plotted now as a function of age. Again, the canon is low alpha is young, high alpha is old, and sure enough, most high alpha stars are old, but these young ones exist, they're in there, that's that second little group. And the other one is that you can also measure the age distribution and the mean age for the first time within the low alpha sample well. You can actually measure age gradients within that chemical population. The latest effort I recommend to you is a really, really pretty effort that involved Ted Macrith, a collaborator, who's actually now, I believe, in Birmingham. And what he did is he took the latest catalog we had of some thousands of apogee stars, correlated the properties of these, and produced a map across the galaxy of almost 400,000 objects where we could both measure Gaia kinematics, measure high-resolution abundances, and we could infer masses and ages from seismology. So we have the full phase space information for this very, very large catalog of objects. When we put this all together, you actually can have a really, really striking pattern here. A living Milky Way galaxy where you can see clear kinematic distinctions between the thin and the thick disk, which have different ratios of the vertical to the radial velocity dispersions. They're clearly very distinct populations. You can see radial trends in the velocity dispersion, which you can actually argue are tied to things like the heating mechanisms for objects in the galactic disk. So you're actually now really able to put all of the pieces together and make real models of the galactic potential, the stars and how they move in it. It's going to be a beautiful, beautiful data set for reconstructing our own kind of breathing Milky Way in a way that's quite different. There's a couple other little things I wanted to get here before I got finished up by talking about Gaia. My original interest in this is I'm a stellar structure theorist, even though it doesn't seem that way some of the time. That's actually what I do. And I was interested in using this to test stellar structure theory. And there's two really beautiful tests of stellar structure theory we've been able to do with this data. The first of which is I now have thousands of red giants where I know the mass, I know the chemical composition, I can infer the age, and I can test my tracks and isochrones and see if they're in the right place. And the bottom line is we found pretty clearly that in general they are not. And by the way, we see the same thing on the main sequence in the Kepler field. I think this is a general phenomenon. The lines represent the theoretical width that you would predict for the distribution, the range of tracks, and you notice even visually here that the width of the red giant branch bundle is too narrow in the data as compared to the theory. This is a sign that we're incorrectly predicting the metallicity dependence of the location of the red giant branch. This is a model-dependent statement, and so we did this and said that if you did this, we basically saw a clear, stretch in our models. There's been several other papers pointing out that the actual shape and zero point of this depends upon your physics in the giant branch models, which is completely understandable. Different physics will put these things in different places and have different stretches. This is, by the way, not accounted for in theoretical models applied to, say, external galaxy populations and will impact integrated light observations that you take because the properties of these integrated light observations are very sensitive to the colors you assign to the giants. The physics here, the idea is that these are all solar calibrated. And from my point of view, there's no reason at all to assume that the mixing length A has a physical justification and B is a universal constant calibrated on the sun. It's convection, right? And so it could be convection. You could also say, well, maybe it's low temperature opacities, and maybe the metallicity dependence of the low temperature opacities is not quite what we see. Not in this gravity domain. No, mass loss wouldn't change this significantly. The other thing that it could be is that you could make some arguments that some model atmospheric boundary conditions we use. Some people use very simple model atmosphere boundary conditions, and you should use more sophisticated ones which can stretch this out. And so there are physical things you could do to change this, but the point is that you have real issues that we can identify. A much more glaring problem to me, and this is something that a paper I've recently submitted with Do-Kun on, is we took the simple exercise of just taking everybody's published core helium burning models, everybody's published red clump models, and we just overlaid them on top of each other, okay? And they do not agree, right? These are all these different models that people use, Parsec, MESA, MIST, whatever it is. And you can notice that in the theoretical plane, there are significant differences in the predicted luminosities of the zero-age horizontal branch. If you compare these to star clusters, this is the real location of M67. The squares reflect the fact we know the mass of M67, and these things do not lie in M67. They lie even less on the metal-rich cluster NGC 6791. And if we were to use the HR diagram position to compute masses based on public tracks, we would get masses that would be almost a factor of 2 low compared to the data relative to the real asteroseismic measurements. And so our conclusion is that the tracks do not agree with one another, nor with the data, and therefore, as a result, there are interesting systematics that have to be traced out in our theoretical models of core helium burning. Constantino and collaborators made similar arguments based upon the period mode spacing on the clump, which is a predicted feature of the structure. So this is a place where our models differ from each other and where we're finding interesting problems relative to the data. In the last bit, I'm going to turn to Gaia, which gives us a beautiful way to check our math on this by giving us a completely independent method of inferring radii. This is showing you the full sample of stars, almost 25,000 stars in the Kepler field, where we have good Gaia parallaxes, good apogee spectra, which means we have abundances, we have gravities, we have temperatures, and we have detailed asteroseismic information. And for all of these, we actually also have seismology. And so the idea here is that Gaia is a beautifully complementary test of structure to asteroseismology. The chain of logic goes like this. I have an apparent magnitude in Gaia. I have a distance I infer from geometry. I have a bolometric correction and extinction that gives me an L. L and TEF from spectra gives me an R. And I can therefore check my asteroseismic radii with a completely independent method with completely different systematics. The other thing you can do here, and this goes to your question about using the frequency of maximum power as opposed to the frequency spacing, if I have an external radius, I can basically measure a mass without using the frequency of maximum power. I can use the frequency spacings plus a Gaia radius to get a mass, right? And so as a result, I can make separable tests of the scaling relations. The other thing you can do is you can say, I believe seismology and test Gaia. And we've done both tests in both directions, as it turns out. Now, testing seismology with Gaia is the first bit, and this is a bottom line summary of what we found in a paper we're about to submit to the APJ. The gray bands represent mean bins of dwarf and subgiant asteroseismic properties. The black bands are red giant seismology. This is the difference, the fractional difference in radius between radii inferred from Gaia and the radii inferred from asteroseismology. The gray band represents 1% agreement in the mean, and the two systems independently agree to one another within about a fractional uncertainty of 1%. This indicates that our mean 0 point is good to that. And
Black bars and the gray bars don't really overlap.
well, there's a limited domain where they overlap, yeah. They're distinct data sets. One of the problems is that most of the dwarfs are near the main sequence and most of the giants are not. There's a kind of a gap in the coverage for technical reasons. These differences down here, by the way, represent basically published state-of-the-art differences. And so if you want to ask how well can we measure the properties of stars, different luminosity choices give you differences at sort of the 2% level, different radius choices at the 1% level, different temperature choices at the 0.5% level. That represents how well we can measure stars. So basically, I would contend that right now the state-of-the-art in stellar astrophysics is at the 1% level, which on the one hand is pretty good. On the other hand, we could probably do better, and so we probably do have to do better to take full advantage of this.
So
Sorry, you're talking about mean agreements 1% is tiny, but the spread is so large. What's that spread?
This is probably telling us about the stellar physics. What we think is happening up here is we think this is where non-adiabatic effects are starting to modify our pulsation properties, and that we're starting to see clear evidence of a deviation in the luminous stars. I'm working on this now with Rich Townsend and Lars Bildsten, where we're looking at non-adiabatic pulsation effects as possibly causing a defect here. This is random scatter, mostly up and down. Individual data sets. So these are the bin means. These are the bin means of these samples. The other issue is that the other thing that limits our precision here is it turns out that there's spatial correlations in the Gaia parallaxes, and those limit our ability to just divide by root n arbitrarily. In other words, we can't do that in this small spatial domain. Individual masses have random uncertainties in the 4 to 7% range. Individual radii 1 to 2%. The vertical spread here is almost all from Gaia, actually, not from seismology. Yes, that's the Gaia. The Gaia parallaxes for these stars are typically about 500 microarc seconds. Yeah, so the parallax errors are almost all this spread is not seismology; it's parallax. But you can see these radial trends, which are telling us about stellar physics and the interpretation in objects of different radius. So at the largest radii appears there's a real defect, and we, by the way, see the same thing when we look in interferometric data. So it's not just in the Gaia parallaxes. We see almost no metallicity trend, which is really striking. And the other thing you can do is you can plot this up as a function of parallax, and this is the work that we did with Joel Zinn, demonstrating that there's a 0 point between Gaia and Asteroseismology of about 53 microarc seconds. Joe and collaborators have come up with a very similar number with a very general argument. And in fact, other people have looked at the red clump and gotten very similar answers. So the idea here is, again, if I compare objects with low and high parallaxes and I have an independent distance estimate, I should basically any physical error in my independent distance estimate ought to scale, like is indicated by these things with parallax. The real trend is almost independent, and that's a sign of a parallax 0 point shift rather than an error in the physics of the calibrator, basically. This will hopefully be something that's removed in the next level of Gaia. The technical cause of this is actually a flexure or a bending in the basic angle between the two Gaia mirrors, which has a periodicity that mimics a parallax signal. That's basically what they're looking at there. And this is at the 50 microarc second level. We also see almost no metallicity trend, which is striking because, again, theoretically, you might have expected these. There's been some published arguments that since the sound speed scales as the mean molecular weight, that's neglected in all these scalings, that actually ought to show up in here. And we don't see any evidence that it is. And finally, when we look at the halo stars, we do see an improved agreement. The scaling relationship masses now are down to closer than they used to be, but they're still too high. And we believe that this reflects, if we use Gaia radius and delta nu, we get an answer that's extremely accurate. So we think that the frequency of maximum power scaling is actually breaking down in the most metal-poor stars. That is to say that for whatever reason, you can't assert that the acoustic cutoff frequency scales to the sun without a metallicity-dependent term, which is not necessarily physically surprising. Fortunately, from my point of view, it turns out that we are not yet put out of a job by this chemical tagging. One of my favorite results in the Macareth paper is I went back and forth with Ted on this, and the basic issue is if you feed these pipelines old ages, they do not return old ages from the chemical tagging. And the problem appears to be that in the most metal-poor stars, the chemical evolution trends are tangled with the age trends, or they dominate the age signals in such a way that even the robots can't extract an age signal from the very, very old stars. And that means that we can't be completely calibrated out of existence. You actually have to continue making astroseismic measurements to actually get ages of individual stars older than about 8 gigayears. It appears that appears to be the boundary where the chemical tagging breaks. And it took a while for Ted to convince me that this was, in fact, the robots were really, really good, so it wasn't that the robots were just searching in a false place of phase space. Now, there is this test satellite that came through, and I'm just putting this up to indicate that we have a future for this. The TESS team just released the first 2 segments of data containing 1.7 million individual light curves from the full frame images of the first 2 of 26 sectors. This represents the volume of data we think we can extract. This is we believe that when the dust settles, we'll have of order 1 million asteroseismic signals from the test satellite. The exact number depends upon how far down in the luminosity domain we can actually dig a signal out of, and so it's going to be at least hundreds of thousands and could be 1 million or more. This is in a fit of foolishness. This is also something we indicated we could do, and so we have promised NASA we're going to try and do the astroseismic analysis for all these stars. Initial signs look promising, although this is clearly a case again for the robots, because no matter how many graduate students you have, you're probably not going to look at 1 million individual light curves. Although, frighteningly enough, people do look at 10,000, which I find already actually quite sobering in and of itself. And this is kind of showing you the characteristic magnitude distribution. These are the magnitude distributions of the individual postage stamps from tests, the ones we observe on the full frame images. You're also seeing here basically the noise characteristics, which in the best case are getting very close to the noise floor. So the bottom line is TESS is working as advertised. I'll summarize by saying we have Kepler, we have K2, which I was barely able to touch on, Plato, which is coming up, and W first, all of which are going to be doing astroseismology. This is something that is now a working tool. I hope I've convinced you that you can measure this to high precision in individual cases, that we can understand the systematics, and that the masses and ages we produce should be taken seriously. There is work to do, and it's a terribly fun time to be working in this field, and thank you all very much for your attention.
We have time for a few questions.
You said that you prefer to use the carbon oxygen ratio contracted.
Yeah.
Because you said you understood that the processes that it's coming from.
Yeah.
But
Yeah.
is it clear that mass loss from winds can't change along this ratio?
In the giants we're looking at are low on the giant branch, where there's no class of theoretical models where you expect significant mass loss to occur. Now the place where it will happen is binary mass transfer. There's going to be a subcategory of binary mass transfer stars that are weird in all of these diagnostics.
The heavier elements are overrepresented in winds.
Oh, no, in this case, because the convection zone has been dredged up, almost a huge amount of mass, more than half a solar mass is in the convective envelope, and so selective losses and things. It's also why gravitational settling, which is actually a serious problem near the main sequence, doesn't affect our answers significantly, because you've dredged up and homogenized the outer half or more by mass of the star.
Yeah. So for the pump stars, do you think you're beginning to probe biases originating in the theoretical field of the flash?
Yeah. One possibility for getting the luminosity wrong is that we're estimating an incorrect mass of the helium, mass at helium ignition, right? Which would be testing the physics of the helium flash and the luminosity at which it occurs. Or the core mass at which it occurs, at least, relative to the luminosity. Another possibility is the helium enrichment scenario, which actually could change that. And another is that the core helium burning stars actually have a convective core, which is surrounded then by an inert layer and then another shell. And the treatment of that boundary layer, the cavity we're looking at, is actually not the convective core. It's the reason outside of it, and the treatment of that boundary layer may be inadequate. Right, so it may be reflecting our treatment of the boundary effects in convection that are failing in terms of our modeling. It appears the lifetimes have to be quite a bit longer than we thought they were to fit the data. Yeah.
So you showed this, you comparing isochrones.
Yeah. Yeah.
Are we at a stage where you actually have to use non-solar mixtures of metallicity rather than just solar scaling up and down?
Yes, I think it's clear that the theoretical models are going to have to do that. It's already, for example, when we're looking at the detailed modeling, the comparisons of isochrones against giants, many of the existing classes of models don't even allow alpha enhancement. They just have some formula from Solaris that's 20 years old where they kind of pretend that you can treat it as iron, and that doesn't actually work in detail. So you definitely need at least a two-dimensional system of alpha and iron. And it's also pretty clear, I suspect that these mismatches we're seeing in part arise from the fact that the mixture itself is changing too. One piece I didn't have a chance to discuss is I told you we measured the red giant branch bump in our data. I didn't mention the fact that it's in the wrong place, but it is. It's in the wrong place. And that reflects a defect in the models. So sorry here. This luminosity is really obvious. The theoretical luminosity is here, right? So it's actually in the wrong place. And we think that that may reflect the fact that, for example, we aren't using the correct opacity mixtures. We dredge up nitrogen in this domain, and none of the models include extra nitrogen opacity in the calculations.
That is, that's one more free parameter, or one couple more free parameters you produce.
Well,
So that means,
well, it's not a free parameter because it's measured in the data.
if you also have alpha.
Yeah. But so it's saying that you have to have these measurements, but the point is we should check. Maybe the mixture cancels out and we're lucky, but I doubt it. That's almost never been the past history in the field.
Okay, so if any of you have any further questions, we can continue discussing with Marc upstairs. Also, we're going to take Marc for dinner tonight at 6. We're almost full, but if there are students actually that want to join, there are certain spots. I was going to thank Marc again.
Thank you.